In this section, actually this chapter, we go back and look at lines in the plane again, but this time looking at them from the point of view of functions. Okay, so when we see the graph of a line, we're going to try to associate it to a function, and we're going to be using functions or linear functions to do some modeling and problem solving. So I'll just remind you what the equations of lines in the planes are. There are like two types that we're going to be using here, the slope-intercept form and the point-slope form. So maybe let's start with y equals mx plus b. Is that point-slope form or slope-intercept form? Yeah, that's slope-intercept form. For example, if you've got y equals 4x plus 2, 4 is your slope, and 0, 2 would be your y-intercept. Okay, so 0, 2 would be the y-intercept, and this coefficient which multiplies x is the slope. So this is slope-intercept form. And on a graph, okay, we'd have a line passing through 0b, and it would have a slope of m, which means that if you go forward by 1, you go up by m. So make a right angle. Okay, so that's what a slope of m means. There's another form. So this is the first form. So two forms for lines. Okay, this is number one. Number two, we've got the point slope form. So this is when we're given a point in the plane. Let's call that point x0, y0. And we're given a slope. So we know that if we go forward by 1, we go up by m. And that completely specifies a line. Okay. So the equation of that line is y equals m times x minus x0 plus y0. Sometimes we also send the y0 on the other side, but here, since I want to take these equations and look at them from the point of view of functions, I want to have a y solved for in the equation. So that's our second. So here, example, if I have a point that's 1, 3 and a slope of 4, the equation would be y equals 4 times x minus 1 plus 3. Okay, so this would be if it goes through 1, 3 with a slope of 4. Okay, but now essentially to look at those graphs from the point of view of functions, we're going to replace y by f of x. So y is going to be our output. I'm going to write that as a function value. So now we're going to have f of x equals either, this is in points in slope-intercept form, mx plus b, or f of x is mx minus x0 plus y0. Okay, so maybe I'll write something like, let's consider the lines to be the graphs of functions. This is lines here. Okay. And we're going to call those functions linear functions. Okay. These functions are called linear functions. Okay. So we're going to look at a first problem. Okay. So in this problem, we've got a train that passes in front of a station without stopping, okay? And then you're actually standing next, 250 meters away from the station, okay? And then you start recording the train's position as a function of time by measuring how far it is from the station. So initially, when it passes right in front of you, that distance is 250, but then it moves away from the station, so that distance is going to be increasing, and you're keeping track of the for maybe using a drone, I don't know, of the distance between the train and the station. So here are your data, the data that actually you recorded. So when t is 0, so initially when a train passes right in front of you, it's at a distance of 250 meters away from the station. 1 second later, okay, so this data is part of the problem, not calculating anything, okay, so 2 seconds later it's 416, 3 seconds later it's 499 meters, okay. And you want to model the distance as a function of time. So maybe you want to know, like, by how much, like, the distance increase in 1 second, and then you realize it has gone up by 83 meters, okay. And then you look at how much it's gone up between the first and the second, and actually it's still 83 meters. And here also 83 meters. Okay, so each time you've got a function like this which increases constantly, like at a constant rate, between equally spaced points, okay, you're going to be dealing with a linear function, a function whose graph is a line. And maybe let me try to convince you of that. So if we illustrate on a diagram, this is t and this is the distance. So initially we're at 250, okay. Now, the fact that it increases by 83 means that if we go forward by 1, we're going to go up by 83, okay, after 1 second. After 2 seconds, if we go forward by 1, we go up again by 83. And between the second and the third, if we go forward by 1 second again, we're going to go up by 83 again. Okay, so that shows us that our lines, they're actually aligned. They're all part of the same line. Okay, it's the same increase for each second. Okay, so our points are equally spaced, like 1 second apart, and then the increase is 83 meters in that case, right? So this is in seconds, this is in meters, okay. And maybe we're going to write this down because that's kind of important. So note, we've got a constant slope. It's basically between each point, okay. So constant slope between each point, constant slope, because when we go forward by 1, it's always going up by 83. Each point, this means you've got a linear function. Okay. We can also see it by a constant incrementation, okay, between equally spaced points, means it's a linear function. So I'll write that too, it's kind of equivalent here. Constant incrementation between equally spaced points. Okay, that means you're also dealing with a linear function. So whenever you see this, you should be using a linear model. So if you've got your data like this, okay, and you look between equally spaced points, like if it's going up by the same amount each time, it's linear. So of course, be careful, right? If you've got a table that'd be, I don't know, 0, 1, and then all of a sudden 1.5, okay, and then 2, Of course, between 1 and 1.5, it's not going to be the same increment. Than between 0 and 1 or 1 and 2. So between 1 and 1.5, okay, if it's linear, it's going to be going up by half as much as it did between 0 and 1. So it would be going up by 83 over 2 instead, right? And then 83 over 2 between 1.5 and 2. So if that occurs, well, between each point now we've got constant slopes. Maybe it's easier to look at the slopes, okay? So the slope here between the first and the second data point would be 83 delta y over delta x, so 83. But between the second and the third point, right, it'd be an increase of 83 half over 1 half, which would give you 83 again. So there's a constant slope between each point here. So if you don't have equally spaced points, well, you're not looking for constant incrementation. So what's the equation of our line, and what and by finding that, we're going to find what our function d is. So here the slope, right, is clearly 83. The y-intercept is clearly 0 to 50. So we've got a slope, a y-intercept. So we can write down the equation of our distance in slope-intercept form. So it's going to be 83t plus 250. Okay, and that's in meters, right? So D has units. Maybe I'll also want to show you that M has units. So for example, calculating M here, we could use 2 data points, but actually we know that the incrementation is 83 for each step of 1, so it's pretty clear the slope is 1. But let's say we forget about that for a second. Let's say we actually use, let's say, the second and the third point to find our slope. What would we be calculating? We'd be calculating, we would have done, I don't know, 416 minus 333 over 2 minus 1. Okay, we would have obtained, of course, 83 up there. That's in meters. Okay, and below it's seconds minus seconds, that's seconds. Okay, so our slope is actually 83 meters per seconds. So it has units. Okay, so in particular, if you're given information about a function, and then somewhere in there's something where it's units per other units, probably that's going to be a slope, because a slope is a ratio of y over x, right? Delta y over delta x. So it's going to be something per something. So here, meters per second. It reminds us also that a slope here for a linear function is an average rate of change, but that change is, well, the average rate of change is the change anywhere on the curve. So it's a line is a curve that has a constant rate of change. So if you remember average rate of change, those had units as well, some things per something. Well, it's the same thing with your slope. And maybe one last comment. Please, please, please do not use f if the function has some other name. Here it's d. Do not use x if the input has some other name. Here the input is t for time. Okay, so don't write something like this. Okay, you're going to lose some marks. So I'm going to take off marks for notation. So if you start like jumping around between names for your inputs, okay, you want to use the same input all the time. So t was chosen, right? That's what we have on our x-axis, like it's a t-axis, so it should be a d of t and not an f of x or, okay, anything like that. Okay, so try, avoid using this if you were actually told what to use for the name of the function and the name of the input. If you're given a choice, maybe you can use it, but at the same time, if your input is time, it's easier to use a letter that's related to the word time. Same thing for your function. If you have a function and it represents distance, why not use a letter, d, or you could use capital or lowercase letter d, I don't care. but use a letter that's linked to the word you're trying to represent. So this would be something to avoid last time. I'm going to erase it.